Welcome to the 11th and the last program on electromagnetics. Today we shall be discussing the time varying fields. In this program, we shall start with the Faraday's and Lenz's law of electromagnetic induction, which would be followed by a discussion on transformer and motional EMF. Thereafter, we shall talk on displacement current given by Maxwell, which would be followed by a discussion on point and integral form of Maxwell's equation, and finally the time varying fields and the Lorentz equation. In our previous programs, we have talked about electrostatics and magnetostatics, where the field was a function of space only. It was not a function of time. And when we talked about electrostatics, we encountered only the electric field intensity and the electric flux density. And when we talked about magnetostatics, we talked about magnetic field intensity and magnetic flux density. Thus, while discussing electrostatics, there was no mention of any vector involving magnetostatics, and while studying magnetostatics, there was no mention of any field involving electrostatics. That is, the fields were independent of each other. Now, in time varying field, we shall encounter both the electric and magnetic fields, and both would be functions of time. A time varying electric field is produced by charges moving with acceleration or by time varying current or alternating currents. Coming to the Faraday's law, in 1820, Oersted had performed an experiment through which he was able to demonstrate that a steady current produces a magnetic field. Faraday, who also belonged to the same era, felt that if electricity could produce magnetism, then the reverse should also be true, and he carried out number of experiments, and finally in 1831 he was able to prove that electricity could be generated from magnetic field. According to Faraday's experiment, a static magnetic field produces no current, while a time varying magnetic field produces an induced voltage in a closed circuit which causes a flow of current. The Faraday's first law of electromagnetic induction states that whenever the flux linking a coil or conductor changes, an EMF would be induced in it. In the Faraday's second law on electromagnetic induction, it states that the magnitude of the induced EMF is proportional to the rate of change of flux linkage, which is given by VEMF is equal to minus d lambda by dt, which is equal to n into d phi by dt. Incorporating Lenz's law, this expression becomes VEMF is equal to minus d lambda by dt, which is equal to minus n d phi by dt. The negative sign shows that the induced voltage acts in such a way as to oppose the flux producing it. According to Lenz's law, the direction of current flow in the circuit is such that the induced magnetic field produced by the induced current will oppose the original magnetic field. Now, it has been described that an electric field is one in which electric charges experience force. That is, the electric fields are caused by electric charges. In such fields, the flux lines begin and end on the charges. However, there are other kinds of electric fields not directly caused by electric charges. These are EMF produced fields, and the EMFs are produced by batteries, electrical generators, thermocouples, photovoltaic cells, etc., which all convert non-electrical energy into electrical energy. It should be noted that the direction of EMF produced field are from negative to positive, while that of field produced by charges is from positive to negative. Now, consider the circuit shown in figure 11.3, where there is a battery connected to a resistance and a current I flows in the circuit. As can be seen, there are two EMFs. One is inside the battery, which is given by EF and which is due to the electrochemical action of the battery, and the second is EE, which is throughout the circuit. The total electric field at any point is given by E is equal to EF plus EE, given by equation 11.2, and if we integrate throughout, we get the expression E dot dl for the closed path L, which is equal to EF dot dl, the integration being carried out from N to P. It can be seen that the integral EE dot dl vanishes because EE, or the electric field caused by the charges, is a conservative field. The EMF of the battery is the line integral of the EMF produced field, that is V EMF is given by integration from P to N of EF dot dl, which finally comes out to be Vp minus Vn, given by equation 11.4. Next we come to the transformer and motional EMFs. From Faraday's law, V EMF is equal to minus of d lambda by dt, which is equal to minus of n d phi by dt. If n is equal to 1, then the equation reduces to V EMF is equal to minus d phi by dt. In terms of E and B, equation 11.6 can be written as given by 11.7, which is V EMF is equal to E dot dl, which is equal to minus ddt of B dot ds. Here phi is nothing but the surface integral of B dot ds. Now it can be clearly seen that in a time varying situation, both electric and magnetic fields are present and are interrelated. The variation of flux with time can be caused by any of the three ways mentioned below. Number one, by a stationary loop in a time varying magnetic field, by a time varying loop in a stationary magnetic field, and third, by having a time varying loop in a time varying magnetic field. We shall now discuss each of the three cases. The first case is of a stationary loop in a time varying magnetic field, as can be seen in figure 11.4. The value of V EMF is given by equation 11.8, which is minus of surface integral of del B by del T dot ds. The EMF induced by the time varying current in a stationary loop is often referred to as transformer EMF in power analysis because it has been produced by transformer action. If we apply Stokes' theorem, the line integral gets converted into a surface integral, and on comparing the two surface integral, we get curl of E is equal to minus del B by del T, which is one of the Maxwell's equation in time varying fields. It shows that the time varying field E is not conservative, as was seen in the case of electrostatics. This, however, does not mean that the principle of energy conservation are violated. The work done in taking a charge about a closed path in a time varying electric field is due to the energy from the time varying magnetic field. Second is the case of a moving loop in a static magnetic field. When a conducting loop is moving in a static magnetic field, an EMF is induced in the loop. Now, the force on a charge q moving with velocity u in a magnetic field is given by Fm is equal to Qu cross B. We define the motional electric field Em as Em is equal to Fm upon Q, which is equal to U cross B. If we consider a conducting loop moving with uniform velocity as consisting of large number of free electrons, the EMF induced in the loop is given by equation 11.13. Such an EMF is called motional EMF or flux cutting EMF because it is due to the motional action. This is the kind of EMF that we encounter in transformers, generators, motors, etc. Another example of motional EMF is a rod moving between a pair of rails as given in figure 11.6. Now, equation 11.11 can be written as Fm is equal to Qu cross B equal to IDL cross B, or Fm can be written as BIL because U and B are perpendicular. Equation 11.11 can be written as VEMF is equal to line integral of UB dl, or VEMF is equal to UBL. If we apply Stokes' theorem to the middle and last term of equation 11.13 and simplifying, we get the expression curl of EM is equal to curl of U cross B. The third case is the most general case, which is of a moving loop in a time varying magnetic field. Here both the transformer and the motional EMF would be present. The total EMF is given in equation 11.16, where on the right hand side we have the surface and line integral. If we apply Stokes' theorem to the line integral terms, we finally get curl of E is equal to minus del B by del T plus curl of U cross B. Equation 11.16 and 11.17 can be regarded as the most general expressions from which the expressions derived in case A and B can be derived. Next we come to the displacement current. In program 5, we had come across three currents: the convection current, the conduction current and the displacement current. In that program, we had talked about the former two currents. In this program, we shall be talking about the third current, which is the displacement current. In the last section, the Maxwell's curl equation for electrostatic fields was modified for time varying fields. On similar grounds, we shall now consider Maxwell's curl equation for magnetic fields for time varying conditions. Now, for static electromagnetic fields, we have curl of H is equal to J. Now, we use an identity that the divergence of curl of any vector is equal to 0, or divergence of curl of H is equal to 0, which is equal to divergence of J. But from continuity equation, we also know that del dot J is equal to minus del rho V by del T, which is not equal to 0. Hence, equation 11.18 and equation 11.19 are incompatible for time varying conditions. Therefore, some manipulation is required. Now, equation 11.18 has to be modified to agree with equation 11.19. So, we have to add a term so that equation 11.18 becomes curl of H is equal to J plus JD, where JD is yet to be defined. Also, the divergence of the curl of any vector is 0. Therefore, divergence of curl of H is equal to divergence of J plus divergence of JD equal to 0. For equation 11.22 to satisfy equation 11.20, we have del dot JD is equal to minus del dot J, which is equal to del rho V by del T, which finally comes out to be divergence of del D by del T. If we compare the first and the last term of equation 11.23, we get JD is equal to del D by del T, and equation 11.21 now becomes curl of H is equal to J plus del D by del T. This is another Maxwell's equation for the time varying field. Both the Maxwell's equation that we have encountered are curl equations. The term JD is equal to del D by del T is known as displacement current density, while J is known as the conduction current density. The insertion of JD into equation 11.18 was one of the major contribution of Maxwell's, without which electromagnetic wave propagation would not have been possible. The displacement current can therefore be defined as ID is equal to surface integral of JD dot ds, which can be written as surface integral of del D by del T dot ds. It should be noted that displacement current is a result of time varying electric field. Let us now understand the significance of JD or ID, for which we need to focus on figure 11.7a and b. If we apply Ampere's circuital law to 11.7a, we get H dot dl is equal to I enclosed is equal to I, where I is the current through the conductor and S1 is the flat surface bounded by L. If we use the balloon shaped surface S2 that passes between the capacitor plates in figure B, then H dot dl would be equal to I enclosed would be equal to 0, because no conduction current flows through the capacitor. This is contradictory to the fact that the same closed path L is being used. To resolve the conflict, we need to include the displacement current in the Ampere's circuit law. The total current density is J plus JD. In equation 11.27, the displacement current density JD is equal to 0, while in equation 11.28, the conduction current density J is equal to 0, so that H dot dl would be equal to JD dot ds over the surface S2 is equal to ddt of d dot ds is equal to dq by dt is equal to I. Hence, you obtain the same current for either surface. However, it is conduction current in S1 and displacement current in S2. The following conclusion can be drawn regarding the displacement current. The displacement current and the conduction current, though discontinuous, but when they are in different part of the circuit, they have the property of continuity. Secondly, the displacement current is precisely equal to the conduction current when they are present in different parts of the same circuit. Thirdly, just as a conduction current produces a magnetic field, in a similar way, the displacement current also produces a magnetic field. And lastly, the displacement current is a result of the rate of change of electric flux. It can be seen in the figure that there is a capacitor, and in between the plates there are two fields. One is the electric field while the other is a magnetic field. The time varying electric field between the plates of the capacitor is directed perpendicular to the plane of the plates, and the time varying magnetic field produced by the electric field is along the perimeter of a circle in a plane parallel to the plate of the capacitor. Thus, the time varying electric field and the time varying magnetic field are perpendicular to each other. The concept of displacement current is connected to the propagation of electromagnetic waves. Thus, the varying electric field and magnetic field are transverse in nature is a feature of electromagnetic waves. Next, we come to Maxwell's equation both in the point and integral form. It was Maxwell who put forward the unified theory of electricity and magnetism. He introduced the displacement current and predicted the existence of electromagnetic waves. Now, from Faraday's law, curl of E is equal to minus del B by del T, and from Ampere's circuital law, curl of H is equal to J plus JD, which is equal to J plus del D by del T. The slide shows the generalized form of Maxwell's equation. It should be noted that the divergence equation in the time varying fields are similar to the ones which were developed for the electrostatic case and the magnetostatic case. However, the curl equations are modified. The first equation, that is del dot D is equal to rho V, it is the Gauss's law. The second, del dot B is equal to 0, it shows that an isolated magnetic charge cannot exist. The third, curl of E is equal to minus del B by del T, which is the Faraday's law. And the fourth Maxwell's equation, which is curl of H is equal to J plus del D by del T, it is the Ampere's circuital law, or rather the modified Ampere's circuital law. The physical interpretation of Maxwell's field equation. Del dot B is equal to 0 indicates that the net magnetic flux emerging through any closed surface is 0. Del dot D is equal to rho V shows that the total electric flux density or total electric displacement through the surface enclosing a volume V is equal to the total charge within that volume. The third and fourth Maxwell's equation indicate that a time varying electric field gives rise to a time varying magnetic field, and a time varying magnetic field gives rise to a time varying electric field. These two curl equations form the basis of electromagnetic wave propagation. Lastly, we come to the retarded potential or the time varying potentials. First, we shall discuss the concept of time delay. We are all aware of the fact that the light that comes from the sun to the surface of the earth takes around 8 minutes. Or in other words, the light that started from the sun at 9:52 would be observed by us at 10 am. Thus arises the concept of time delay in electromagnetic waves. Now, during a study of electrostatics and magnetostatic fields, it was found possible and convenient to first set up potentials in terms of the charges or currents, and then to obtain the electric and magnetic fields from these potentials. Similarly, in the time varying electromagnetic fields, it would turn out much simpler if we could set up the potentials that are related to charges and currents, and thereon to obtain E and H from these potentials. There can be two ways of doing this. One is the heuristic approach and the second is the Maxwell's equation approach. We shall first see the heuristic approach. This is nothing but an approach which goes by analogy. Just as in electrostatics, a scalar potential V was set up related to the electric charge distribution given by equation 11.31a, and from this potential we were able to find out electric field intensity equal to E is equal to minus gradient of V. Similarly, in magnetostatics, the vector magnetic potential was found and related to the source current given by equation 11.31b. From this magnetic potential, we were able to find out magnetic flux density given by B is equal to curl of A. The sources of the electromagnetic field are current and charge distributions that vary with time. So, it is reasonable to try the same potentials generalized for time variations. That is, we can write A and V given in equation 11.32a and 11.32b. From these two equations, we assume that the strength of these potentials vary instantaneously with the strength of the sources. But we are aware that the speed of light is very high but finite and has a value of 3 lakh kilometers per second. That is, it is not infinite. Therefore, there will be definitely some time delay in wave propagation. Therefore, it is logical that the potentials from which the fields are to be derived also display finite propagation time, and therefore, the earlier equations are now transformed by equations 11.33a and 11.33b, where a time delay has been introduced given by t minus r by v, where v is the velocity. In these expressions, a time delay of r by v seconds has been introduced, so that now the potentials have been delayed or retarded by this amount. For this reason, they are often referred as retarded potential. We shall now take the Maxwell's equation approach for determining the field. Now, the Maxwell's equations in time varying differential form, keeping in mind a scalar and constant permittivity and permeability, are given by equation 11.34, that is curl of H is equal to J plus del D by del T, curl of E is equal to minus del B by del T given in equation 11.35, del dot D is equal to rho V or del dot E is equal to rho V by epsilon, and del dot B is equal to 0 or del dot H is equal to 0. Also, we know that B is equal to curl of A. Now, from equation 11.35 and equation 11.38, we get curl of E plus del A by del T is equal to 0. Since the curl of the gradient of a scalar field is identically 0, that is, curl of gradient of a scalar V is equal to 0, the solution of equation 11.39 comes out to be E is equal to minus del A by del T minus gradient of V. Taking the divergence of the above equation and inserting equation 11.36, we get del dot E is equal to rho V by epsilon, or Laplacian of V plus partial derivative of divergence of A is equal to minus del rho V by epsilon. In this equation, it can be seen that in this equation V and E are coupled. Similarly, taking the curl of equation 11.38, that is B is equal to curl of A, and using equations 11.34 and 11.40 and simplifying, we get equation 11.42, which is again an equation where both V and A are present. Thus, we see that equation 11.41 and equation 11.42 are complicated because of the fact that they are coupled, that is, they contain both V and A. A further complication is due to the fact that both these equations do not yield a unique solution for the potentials. The truth of this statement can be inferred from the Helmholtz theorem, which states that any vector field due to a finite source is specified uniquely if both the curl and divergence of the field are specified. The examination of equation 11.41 and equation 11.42, they show that if the divergence A is set equal to minus mu into epsilon del V by del T, then these equations would become uncoupled and would reduce to standard wave equations with the source term included. That is, from equation 11.42, when we put the value of divergence of A, we get the expression given in equation 11.43, that is, Laplacian of A is equal to minus mu into J. Similarly, from equation 11.41, we get Laplacian of V minus mu epsilon del 2V by del T square is equal to minus rho V by epsilon. The particular choice, that is, del dot A is equal to minus mu into epsilon del V by del T, is known as Lorentz equation for potential, and it should be noted that it is not arbitrary. Now, potentials V and vector magnetic potential A both satisfy Poisson's equation for time varying fields, that is, Laplacian of A is equal to minus mu into J and Laplacian of V is equal to minus rho upon epsilon. These are special cases of equation 11.43 and 11.44. The solution of equation 11.43 and 11.44 comes out to be in the form of equation 11.45 and 11.46, where r and the velocity v are given as shown. In free space, the velocity of light is given by 3 into 10 to the power of 8 meters per second. Potentials V and A are respectively called the retarded electric potential and the retarded vector magnetic potential. Once we have the expressions for V and A, the fields B, E, H and D can be derived from this. To summarize, in this program, we have talked about time varying fields, where the fields were a function not only of space but also of time. The fields were interdependent. We started off this program with a discussion on Faraday's law of electromagnetic induction and the Lenz's law. Thereafter, we talked about the transformer and motional EMF. This was followed by a detailed discussion on displacement current and its physical significance. Thereafter, we talked about Maxwell's equation in point and integral form, and finally, a discussion on time varying potentials, including the Lorentz equation was discussed. I hope you have enjoyed this program. Thank you.